In this example, we want to analyze a series that does not have all positive terms and look into its convergence or divergence. So the series we have here is a series from 5 to infinity of sine of n over n squared. And I don't know if this converges or diverges by any method covered so far, and carefully explain the argument for this case. So your first thought here might be that it's n squared in the bottom, and the top is bounded, so it should be like a p-series and should converge. And this is true, this is the right idea. We got to figure out how to properly state it to get this convergence correctly formulated. So what can we say about this? Well, this series does not have all positive terms, right? Sine of n can be both positive and negative. So I can't use direct comparison test here because direct comparison test requires terms to be positive. So what can we do here? We can instead take the absolute value series and see if that one converges. So instead, let's look at the sum n from 5 to infinity of absolute value of sine of n over n squared. And since n squared is always positive, the same thing as the sum from 5 to infinity, absolute value sine of n over n squared. Now that we have all positive terms, we can now do our direct comparison test. So since sine of n absolute value is always less than 1, because sine is between minus 1 and 1, we know that sine of n over n squared in absolute value is less than 1 over n squared, and that series converges. So since sum 1 over n squared n from 5 to infinity converges by p-series, the direct comparison test, since this is positive here, tells us that this absolute value series converges. However, that was not the series in question here. So for the original series, sum n from 5 to infinity of just sine of n over n squared, our previous work shows that this series, which is the absolute value of our series, converges. The previous step showed that the series from 5 to infinity of the absolute value of this term converges. That was our direct comparison test argument. So therefore, my original series converges absolutely, and therefore converges. So the argument is a little bit long-winded here, but you have to use these proper steps to get to an accurate proof of the convergence of this series. For most of these types of problems, usually your gut is correct, right? The gut thought at the start is this looks like a 1 over n squared, so it should converge. And that's a good thought to have. That's a good first impression, and it motivates how you want to do your argument to get to a proof. And so the only catch is, when using direct comparison or limit comparison, you have to actually have a series of positive terms. So you take absolute values. And in this case, thankfully, taking absolute values gives us something that still converges. So therefore, we get absolute convergence for our series, and therefore convergence. So there's an argument laid out for how you would argue that this series here converges using absolute values and a direct comparison test.